Lesson 0.1, Fun with Fractions, Part 5, Working with Fractions Containing Variables. The first 4 parts of this lesson were all arithmetic lessons. This is our first algebra lesson. As soon as you start replacing numbers with variables, you leave the world of arithmetic and enter the world of algebra. Now we're still focusing on the same learning goals, adding, subtracting, multiplying, dividing fractions. The difference here, because we're looking at fractions from an algebraic perspective, it becomes that much more important that you truly understand the rules. It's one thing to be able to add 1/2 plus 1/3 following the appropriate rules of arithmetic with fractions. But if you can do that without knowing what the individual numbers are, the 1, the 2, the 1, the 3, replacing all 4 of those with variables and still follow the same rules, then that tells me that you truly understand what the rules are. If you can do algebra, then you can definitely do arithmetic. It's not so the other way around. So here's the simplest example I can point out to illustrate what I mean by this. So if I want to add the 2 fractions a over b plus c over d, follow the rules of adding fractions. If I'm adding fractions, what do I need? I need a common denominator. One fraction has a denominator of b, and the other fraction has a denominator of d. Well, if I were adding 2 fractions together, and I knew numerically what the denominators were, and I knew that one did not go into the other one, or I just didn't know how many times one went into the other one, I could always find a common denominator simply by multiplying the 2 denominators together. So if I multiply b times d, what do I get? I get bd. It's as simple as that. The product of 2 numbers is the product of those numbers. That's the beautiful thing about algebra. It's so simple. Just follow the rules. So I know the common denominator is going to be the product b times d, and if I multiply the bottom of the fraction by something, I also have to multiply the top. So let's go through that process. So I'm multiplying b times d to get the common denominator, which means I'm also going to multiply the numerator times d. So multiplying a fraction really means multiplying top and bottom of the fraction by that same number. With the second fraction c over d, I'm going to multiply both top and bottom by b. And when I clean up that multiplication problem, I get AD over BD, AD over BD, plus CB over DB, CB over DB. And you'll notice that I often rewrite multiplication problems of variables in alphabetical order. B times C and C times B are the same thing. Now that I have a common denominator, I can add the 2 fractions together by keeping that same common denominator as the new denominator and adding the numerators. But remember, the rules of arithmetic say that you can only add things together if they are the same type of thing. 7 plus 14, 7 and 14 are both numbers, so 7 plus 14 is 21. But if I say 7 inches plus 14 feet, those are not the same type of object, so you cannot add them together. Well, AD and BC are not the same type of object. They are not like terms. In order to be like terms, they have to involve the same variable. So AD plus BC is AD plus BC. If you can't add things together, then don't add them together. Just like if you can't multiply B times D, then the answer to B times D is B times D. And that's it. That's the final answer. I have followed the rules of arithmetic in order to add these algebraic statements together, A over B plus C over D, leaving me with the final answer, AD plus BC over BD. Now, it's a statement like this that leads me into what are some incorrect simplifications, because often statements like this will come up in advanced algebra, and students will think they remember what a rule says and apply what they think the rule says, when in fact, the way they applied it is not the correct way that the rule is stated. For instance, when I'm simplifying a fraction, if you see the same thing on the top and bottom, cancel it out. Well, hey, I don't know about you, but I see a B and I see a B, one on top, one on bottom. So hey, let's go ahead and cancel it out. Now, of course, when I cancel it out, that means it just completely disappears. So I'm left with, instead of BC, it's just C, and on the bottom, it's just D. Well, speaking of which, there's a D on the top, there's a D on the bottom. Let's go ahead and cancel it. And just like we did before, everything disappears. Now, I also remember a rule about when you have nothing in the denominator, that means that there's an invisible 1 in the denominator, but of course that invisible 1 doesn't matter, which means my final answer is A plus C. Now, hopefully you felt as much pain listening to me go through that as I felt saying it, because you already know that what I just did was complete and utter garbage. Because, of course, you understand that rule about canceling something on the top with something on the bottom requires it be written in a specific way. Now, before I get into that, I can easily disprove what I just did here. Anytime you're going through an algebraic simplification and you're unsure as to whether what you did was true, look at what you started with and look at what you ended with. Now, in this case, everything's written in terms of variables, so let's just pick some random numbers and plug it into those variables. Because if a statement is true in its variable form, then that means if I replace those variables with any random number I choose, then it should still be true after I've plugged in those numbers. To say something is true is to say that it's true for all cases. So let's just pick a number for A, pick a number for B, pick a number for C, pick a number for D, and plug it in and see what happens. Now, here's the random numbers I chose, 2, 3, 4, and 5. Notice I didn't choose 1 because a lot of times when you plug in 1, you can actually get a positive result, but in actuality, it's actually not true. So there's special cases with zeros, with ones. I definitely don't want to plug in 0 here, especially if I try to plug in 0 for B or for D, because that would destroy the universe. So when I'm picking random numbers, I usually pick numbers 2 and higher. So I needed 4 numbers, so 2, 3, 4, 5. So here's me plugging in 2, 3, 4, and 5 for A, B, C, and D. Now, by doing that, I would be suggesting that 2 over 3 plus 4 over 5 is equal to 2 plus 4, which is not true. By picking random numbers and plugging them into where I started versus where I finished, I have shown that these statements are in fact not true, which means something in this intermediate space must have been wrong. Now, the misunderstanding usually comes down to these two situations right here. The top one is, of course, true. The bottom one is, of course, false. The rules for multiplication and the rules for addition are not always the same. The issue comes down to what is meant by that rule that says you can cancel something from the top with something from the bottom. Well, what the rule actually says is that you can cancel factors. You cannot cancel terms. Remember, a factor is something that's being multiplied together. 2 and 3 are factors of 6, because 2 times 3 is 6, versus 2 plus 4, which also gives you 6. That does not make 2 and 4 factors of 6. Here, where we're multiplying, A and B are factors of the numerator, which means that you can actually cancel the B, because B is a factor of the top, B is a factor of the bottom. And to further illustrate why that's true, it has to do with properties of multiplication. If I'm multiplying AB over B, that's the same thing as saying A times B over B, because of course we talked about how A is really over 1, A times B gives you the numerator, 1 times B gives you the denominator. So if I have a fraction with extra factors in it, I can deconstruct that fraction by pulling a factor of the numerator out of the numerator as its own separate factor. That does not work with addition. I cannot take the A in the addition problem and pull it out to the front, because this would not produce the same result as over here. I can prove it again just by making up random numbers. A is 2 and B is, I don't know, how about 5? All right, so if I do 2 plus 5, that would be 7 over 5 on the left side, versus this would be 2 plus 5 over 5, which would be 1. Well, 7 over 5 is not equal to 3. So just by picking two random numbers, and I could pick any two random numbers to show that you cannot just pull that number out to the front when it's an addition problem. If I did the same thing up here, it would work just fine. 2 times 5, that would be 10 over 5, which of course is 2. And if I look on this side, well, that's going to be 2 times 5 over 5, which is 2 times 1, which is also 2. So I know it works up here. I can pull that A to the front, but down here I cannot pull that A to the front. This is garbage. It doesn't work, which means you cannot cancel that B term. What you can do, if you see something on the top and something on the bottom, but there's addition or subtraction in the way that doesn't allow you to cancel, what you can do is break it up. just like that. You can break it up into two separate fractions. That idea of common denominators works in both directions. If you have multiplication, you can break up a fraction just by pulling part of it off to the side, keeping it as a multiplication problem, and then you can cancel what's left. But if you don't have multiplication, you have addition or subtraction, as long as you have only a single term on the bottom, a monomial denominator, then you could break it up into two separate fractions, and then you could cancel right there. So this would end up being a over b plus 1. That would be a legal simplification when you see something common between top and bottom and there's addition or subtraction involved. That's perfectly fine. But don't ever let me see you canceling something like this where I see something on top and I see something on the bottom, I just cancel it out because I see it and I want to. Follow the rules of algebra. You can cancel factors, you do not cancel terms. Now, of course, the more you practice that, the less you even have to think about it. All right. Not a lot that I need to talk about in this section because, again, we're just following the same rules that we illustrated in the previous 4 sections. Notice here I've got the one on the left is similar to that sample problem that we just looked at. The one on the right, we're going to encompass some rules that we've used in previous sections. The only difference here is that I'm throwing in variables. Remember, follow the same rules. You just are not going to be able to simplify things as much as you did when you had numerical values. So let's take a look at both of these. Again, follow the same rules that you've been doing all along. Pause here, hit play when you're ready. Let's look at the one on the left. This one should have been fairly simple. The idea is to subtract d over b minus d. Subtraction of fractions means I need a common denominator. Right now, d is over 1, so the common denominator, if I multiply these together, b times 1 would just be b. So if I multiply the top by b and the bottom by b, that's going to give me this as my new fraction, bd over b. They now have a common denominator, so I can rewrite it as a single denominator, and on the top I'm just going to do d minus bd. I'm not going to try to combine those or anything because one of them just says d, the other one says bd. Those are not the same variable. They contain parts of the same variable, but that's not enough. They're not common, they're not like terms, so that's my final answer. I'm just going to leave it alone. Looking at question B, here we have this now familiar fraction within a fraction. Several different ways we can approach this. I'm going to use the technique that I like to use where I simply move the extra denominator either up or down as needed. So when I move the denominators in order to get rid of the nested fractions, I now have this. Now from here you could start multiplying straight across if you want to. I always prefer to simplify first. Things that I notice, I've got an a on the bottom, I've got an a squared on the top. Remember that a squared is really just a times a. So because the a is being multiplied across the entire bottom, this a is a factor of the entire top. So I can go ahead and cancel out a single a from the top and the bottom. Canceling out the single a on the bottom makes it disappear completely. Technically there's a 1 left behind, but I'm not going to write times 1. And on the top, a squared becomes a to the first, which of course is just a on its own. Now I can do a similar thing with the b's, but before I do that, I'm going to group this b to the 5th and b to the 2nd together, recognizing that that really says b to the 7th. And then looking at the b to the 3rd on the top, b to the 7th on the bottom, I can cancel 3 b's on the top, 3 b's on the bottom. That's going to leave b to the 4th on the bottom. Looking at what we've got left, I've essentially got 7a times 21 over b to the 4th. No other common factors between the numerator and the denominator, so let's go ahead and multiply the 7 by 21. Remember, you should not be using a calculator here. 7 times 21, you can do that a few different ways. In your head, you can think of it as 7 times 20 plus 7 times 1, which is really just a distribution of the statement 7 times 20 plus 1, or 7 times 21. 7 times 20, that's 140. 7 times 1, that's 7. Add those together, that's 147. Alternatively, another way I can think to do that one is to recognize that 21 is really 7 times 3. So 7 times 21 is really 7 times 7 times 3. 7 times 7 is 49. And then 49 is really close to 50, but it's really 50 minus 1, which we can then use the same little technique that we did up here. 50 times 3, that's 150, minus 3, which is also 147. When it comes to multiplying in your head, teach yourself to multiply like this, by breaking up the larger number into smaller pieces and then multiplying one piece at a time. Now, of course, you could always just use that elementary school multiplication algorithm if you really want to. I think by multiplying it like this, it's easier to keep track of what you're doing in your head and you don't actually have to write anything down. So, final answer, 147a over p to the fourth. All right, let's up the ante a little bit. Let's throw in some problems involving parentheses. Pause here, play when you're ready. Okay, so what do you do when you see something outside parentheses? You distribute. So it's going to be x times x and x times 3 over x, like this. Now notice instead of saying x times x, I said x squared. And on the second term, the x times 3 over x, recognize properties of fractions. This is really x over 1, which means you can cancel something with the top with something from the bottom. So x times 3 over x is just going to be 3. Final answer. Following the same technique on the second one, distributing the w is going to give me a statement like this. Notice w times 1 is just w on its own. Here, the w isn't going to cancel with anything in the denominator here, so instead we can just multiply the w times the numerator and get 4w over y plus 1 minus w. But we're not done. Just like example A, we had a fraction minus a whole number. We need to keep going. We have a fraction minus a whole number. So let's find our common denominator and combine them. Now in this case, it's w over 1. So I have the quantity y plus 1 and the quantity 1, which means the common denominator is the product of those two quantities, or y plus 1. So I'm going to multiply top and bottom by y plus 1. And I'm writing this incorrectly to begin with because I want to point out every time I see you do this, it annoys me. Here I did not multiply by the quantity y plus 1. I multiplied by y and then I added 1. If you're multiplying by more than one combined object, you need to put parentheses around it. Because w times y plus 1 is not the same thing as w times y plus 1. This one would actually just be wy plus 1, whereas this one is wy plus w. If you have more than one term, you need parentheses around it. So when I multiply top and bottom by that y plus 1 in order to get the common denominator, I have this statement. Now from here I could either clean up the numerator first, or I could just go ahead and combine this into a single fraction. That's what I decided to do. So I rewrote it as a single fraction. Next I'm going to distribute that w outside the parentheses. Now be careful when I distribute that w, it's not just the w, it's also the negative. So negative w times y, negative w times positive 1 is going to give me negative wy minus w. But I'm not done until I'm done. Notice 4w minus w, that's going to give me 3w. And that would be my final answer. And I like that question because it points out, even though there's a lot of steps there, there's no one step that's complex. There's nothing difficult about that question. Just because there's a lot of steps does not make the problem difficult. Follow the rules one step at a time, and when you apply that rule, look to see what else you can do. I didn't know that I was going to have to do a second distribution until I got to this step right here. I did the initial distribution and I thought I was done with distribution. But then as I got through the problem and I realized, oh, there's still a w outside parentheses, I'm going to have a second distribution. I don't know I'm going to need to follow a particular route or follow a particular technique until I get to it. So start the problem, start walking along the path, and wherever the path takes you, just let the path take you in that direction. Now another reason these two problems are fun, in my opinion, is that there's another route that you could have done both of these. Both of these problems I started with distributing, and you may have started that way as well, but I'm going to guess that some people watching this video didn't approach these problems the same way I did. You may have decided, you know what, instead of distributing as my first step, let's go ahead and combine the fractions as my first step. Notice the one on the left, x plus 3 over x, we're just going to completely ignore this and follow the same technique that we did in question A, treat x as x over 1, Common denominator would be x, so multiply top by x, multiply bottom by x, and I get x squared over x. That allows me to combine these two guys into a single fraction, x squared plus 3 over x, and then I can cancel the x from there, leaving x plus 3. Completely different technique, leads us to exactly the same answer. Beautiful thing about algebra is that sometimes you've got choices on which rules to apply, and it's up to you which rules you want to apply. Do you want to start with distribution and go that route, or do you want to start with combining the fractions and go that route? If you follow the rules correctly, then it doesn't matter which set of rules that you follow. As long as you apply them correctly, you will get the same answer. Same thing over here. 1 is, of course, y plus 1 over y plus 1 in order to get that common denominator. Rewrite this as a single fraction, and here's the part that typically trips people up. You have to put parentheses around the y plus 1 because we're not just subtracting the y, we're subtracting the quantity y plus 1. Anytime you're subtracting multiple terms, you need to put parentheses around those multiple terms. Just like if you're multiplying by multiple terms, you need to put parentheses around those multiple terms. Distributing that negative gives me this. 4 minus 1 is going to give me 3, so I now have 3 minus y over y plus 1, and then distributing the w onto the numerator gives me the same answer that I had before. Slightly different route, but exactly the same answer. I don't care which techniques overall that you use, as long as you follow the correct rules. Now, it just so happens that sometimes one set of techniques will get you the answer far quicker than another set of techniques, and there's really no way to know other than experience to know which set of techniques is going to be the best route from the get-go. It's just like if you move to a new city and you want to know how to get from point A to point B, there may be 3 or 4 different routes on how to get from point A to point B, and the person who's lived in that city the longest is going to know the quickest route compared to someone who just moved in there. The key to being good at math is simply experience. Do more practice and you'll ask fewer questions. Speaking of questions, here are 2 more. Pause here, play when you're ready. All right, so what we have here are slightly more complex nested fractions. Again, let's just follow the rules. So looking at this guy, I've got the r, the w, nested in both the numerator and the denominator. I cannot use the trick that I used in question B where I just moved the denominators up and down because of the inclusion of addition subtraction. So the moving of denominators up and down is off the table. But what's not off the table is the technique of clearing the fractions. So let's start by using the technique clearing the fractions. Let's multiply the entire top and the entire bottom by those extra denominators. So instead of multiplying everything by r and then multiplying everything by w, let's just multiply everything at the same time by r and w and see what happens. When I distribute that rw, it's initially going to look like this. And then what's immediately going to start happening is denominators are going to start canceling out. Canceling out the w's, canceling out the r's, and I'm left with this statement right here, 3w minus 4r over 2w minus r. And that's it. You can't go any further than that. Remember, you cannot cancel the r's from here. You cannot cancel the w's from here because of the subtraction. You cancel factors, not terms. W is not a factor of the top because it does not say w times everything else on the top. Sure, it says w times 3, but it's got to be a factor of the entire top, not a factor of just one term. I cannot cancel the w's. I cannot cancel the r's. Final answer. Now, just for kicks, let's look at question E a second time, approaching it a different way. Instead of immediately clearing the fractions by multiplying everything by RW, another option would be to focus on just the numerator and just the denominator separately, combine those two fractions into a single fraction, and then go from there. So instead of looking at everything, 3 over r minus 4 over w, common denominator would be r times w, multiplied by w, multiplied by w, multiplied by r, multiplied by r, and I get this statement right here. Same thing on the bottom. Multiply top and bottom by w, multiply top and bottom by r, I get this statement right here. Combining the numerator and denominators separately into single fractions gives me this. And then remember, there was that trick about if I have a nested fraction over a nested fraction and I have vertical agreement, I can just cancel the b's and I'm left with a over c. Well, that's what we have here. RW and RW are the same denominators, so I'm left with 3W minus 4R over 2W minus R. Exactly the same answer using an entirely different technique. I prefer the clearing the fractions technique, but if you prefer the combining the fractions technique first, I don't care, go for it, whichever one you prefer. Now, if you were stuck on question F, feel free to try that one now. So like I said before, I prefer clearing the fractions. Remember, I can't just move things up and down because of the addition subtraction. So I'm going to multiply everything by the denominators, x squared and x. Now instead of multiplying by both x squared and x, I'm just going to multiply by x squared because the x is part of the factors of x squared. So if I multiply everything by x squared, that will cancel out that extra x. So distributing on the top is going to give me x squared plus 3. Distributing on the bottom is going to give me x squared minus 3x, because of course 1x cancels with the extra x here, so that would just be 3x. Multiplying that entire fraction times 4 really means multiplying just the numerator times 4. Distributing through, I get 4x squared plus 12, which is my final answer. But I will point out an alternative to this final answer, and probably a safer final answer, would actually be this. Instead of distributing through that 4, factor out the x in the denominator. Because just because I've multiplied and added and subtracted everything through does not mean that it's fully simplified, because of course we're looking to fully simplify. And the only way you can simplify a fraction is by canceling out the common factors. So when I have something like this, notice 4x squared plus 12, clearly I can factor out a 4, and x squared minus 3x, clearly I can factor out an x. Imagine if I were to factor out that 4 and factor out that x, and then these two guys were actually the same thing. I would have been able to cancel those out. In this case, they're not the same thing. They're close. They both have the x and they have the 3, but other than that, they're not the same thing, so I cannot cancel them. You should at least be on the lookout for situations like that. All right, here are 2 more. Pause here, play when you're ready. Hopefully question G wasn't too much of a trouble because of how similar it was to the previous 2 questions. I'm going to use the clearing the fractions technique. I have a 5, I have an A, and I have an A, so I'm going to multiply everything by 5A. Distributing that 5A on the top, the 5A times 1/5 is going to cancel out the 5 and leave the A. The 5A times the 1 over A, the A is going to cancel out, and we're going to leave the 5. Notice I didn't write that intermediate step of actually multiplying each fraction times 5a. If it helps you visualize what's going on, go right ahead. But again, as we move forward in algebra, you want to be able to do certain things in your head and not have to write it out. But if you have to write it out, go for it. The more you write it out now, the less likely you're going to have to write it out later. And then, of course, on the bottom, the a's just cancel out, and we're left with a minus 5 times 5, and I distributed that 5 and got 5a minus 25. But that is not my final answer, because if I'm paying close enough attention, I recognize, wait a second, I just multiplied a minus 5 times 5 to get the denominator, and I have an a minus 5 right there, which means I could have actually canceled that a minus 5 and been left with 1/5. So 1/5 is my fully simplified answer. Look for opportunities to factor and cancel. Don't just combine things to get them together. Look for opportunities to factor and cancel. So go ahead and try question H if you haven't already. This one, I designed it to look complex, but it's actually just using all the same techniques that we used on questions A through G. So I'm going to start by clearing the fractions. I see a 7, a 21, and a 3y. I recognize that 21 contains both the 7 and the 3, so I know if I multiply by 21, that'll get rid of the 7 and the 3. And I also need to get rid of the y, so I'm going to multiply everything by 21y. Distributing on the top, 21y times y is going to be 21y squared. And then distributing here, I want to be super careful. 21y times this entire term. So the 21 and the 7, that's going to cancel out and just leave me with 3. So it really says 3y times this quantity. And because it's an entire quantity, 5y minus 7, I'm going to put that in parentheses. It's not just 3y times 5y, it's 3y times the quantity 5y minus 7. On the bottom, a little bit easier, 21s are going to cancel. I'm going to be left with y times 4. And then on the second fraction, the y's are going to cancel. 21 divided by 3, that's going to be 7. So 7 times 2, that's just going to be 14. So the bottom's mostly cleaned up, but we still have some work to do on the numerator. So let's distribute that negative 3y. Again, it is a negative 3y, not just 3y. So distributing that, I'm going to get a negative 15y squared and a positive 21y. Notice I have a y squared, I have a y squared, which means I can combine these two terms right here. 21y squared minus 15y squared, that's going to give me 6y squared, bringing everything else down for the right. So am I done? Is that all I can do? Honestly, I'm not sure, but I do see an opportunity to move forward. So I see that there's a possibility of factoring things out. Notice on the bottom I could factor out a 2, and on the top I could definitely factor out a y. 6 and 21 means I could factor out a 3. So if I do that, what does it leave behind? Well, on the top, factoring out a 3y leaves me with 2y plus 7, and on the bottom, factoring out a 2 leaves me, hey, look at that, 2y plus 7, which means the 2y plus 7 can be canceled out, so my final answer is actually 3y over 2. Unless I actually look for that opportunity to factor, I'm probably not going to know that I'm going to be able to factor. So that's it for this lesson. Go ahead and continue on with the practice assignment posted on Canvas. The key is practice, practice, practice. The more of these types of problems that you see, the more comfortable you are and the easier it is for you to just fly right through them.